We will continue with high order transformations. In the previous lecture, we created a distance matrix, and now we will create the unimodular transformation matrix, which is based on the distance matrix. One can use this for outer loop and inner loop parallelization. And in this course, we will look at inner loop parallelization. Outer loop parallelization is explained in the multi-core programming course, which is given next year. Okay, and we will also look at the sim vectorization in a particular compiler. So, a unimodular transformation is a loop transformation which is completely expressed in a matrix. And what we do is to create new index variables from the original. So we create this transformation matrix, and the new index variables, they are the product of the original and this matrix. What this means is that we will create a new loop nest with the k index variables. And the effect is that we will execute the same iterations, but in a different order. Oh, well, of course, if U would be the identity matrix, there would be no change, but that would not be very useful. We can do this, but it's not certain that the program will be any faster. So this is obviously not a perfect solution to optimize and in particular parallelize programs, but this is the tool that we use to create a different iteration order. Okay, so now we can see why it was essential that the loop transformation matrix is invertible and results in an integer matrix, which it does due to it is a unimodular transformation matrix. We need to express the new loop bounds, and of course we must take the loop bounds from the original loop, and the original loop is this. So we take this expression and put that here and there, and then we can compute the loop bounds for the k loop. And in the previous lecture we tried to eliminate one variable at a time, starting at the rightmost variable. Now instead we want to find the loop bounds of the outer loop first. So we start with finding the bounds for the leftmost variable. Okay, so we have this, that, and put it here, and now we can perform Fourier-Motzkin elimination and find the bounds for the k variables. And as I said, starting with k1 and then expressing k2 as a linear function, bounds with linear functions of k1, etc. So when we then generate the code, the references in the loop, we could start every iteration with recomputing the original index variables, like this. The new loop, when we execute the program, have k, and the compiler certainly knows this matrix. And then we can start the iteration. What I'm saying now is quite ridiculous because it would be extremely inefficient, but just to explain the idea. So we could start each iteration by recomputing the original index variables and use them in each reference. Clearly, we don't want to do that. Instead, we compute what the reference should look like given the original reference, and that is given by this expression. So each reference needs to be regenerated from the original reference and the inverse of the transformation matrix. This is really neat. We have this U matrix and its inverse, and we can take each reference in the code, which is expressed with A and this A, A0, the vector, and simply generate a new loop, a new reference. What I mean is new 3-address code expressed with the k index variables. Okay, as you might know, I have written a C compiler called LMPCC, and it has a function makeref which does exactly this, and it's quite nice to have a complete loop transformation expressed in a matrix.